So I will do something similar for the engine dynamics now. We will capture key features and capabilities of the library. We will look at the example use case. In this case, the use case will be a project that we did with Volvo that is also has been published in the latest Modelica conference. The application is to do model-based control of the gas exchange system of a heavy-duty diesel engine, and with the respect to keep the optimum operating conditions for the exhaust after treatment system. So that is to reduce the transient emissions and to keep the temperature within a suitable operating condition for the after treatment system. We will then look at some of the library contents, and I will show you a demo of the library in Daimler. So the key feature for engine dynamics is the physical gas exchange modeling, and the gas exchange system then includes the manifold volumes and the turbocharging of the engine, also throttle valves and EGR and other intake losses in such as filters and mufflers in the system. The library is based on currently a mean value combustion model. Mean value model means that we do not consider in-cycle effects, and we do not resolve the combustion in crank angle. The models are very flexible in the sense that it's very easy to integrate this framework with in-house combustion models that automotive OEMs may have from previous developments. So the features that must be captured by the combustion models are torque, heat generation, and if you want to study emissions, also that must be included. So the model will then capture both the dynamics and the steady state performance of the engine system. The dynamics would be turbo speed up and also thermal transients. Steady state performance can be used for fuel consumption and so on. It can also capture trends of emission generation. We have a wide range of engine and also generic fluid component models in the system, and there are some templates and examples that will allow users to set up models of their specific system easily. So the key capabilities here is to model diesel and spark ignited combustion engines and capture essential system behavior such as non-minimum phase and sign reversal effects. These are typically limiting effects in the control system development. It limits how fast you can do the control. And I will show you an example of these effects for a diesel engine later on. You can capture the transient exhaust conditions in terms of flow rate and temperature and also emissions. So the transient response in the exhaust that is provided to the after treatment system is quite different from the momentaneous outlet that you get from the turbine. You can do virtual prototyping on the system level, and we have two examples here on the right in this slide. The uppermost is an engine which is compressor charged, so it has a compressor driven directly from the crankshaft or drive shaft. The one below here has a variable geometry turbine, so there's a turbine in the exhaust path coupled to the compressor, and there's a control signal for the geometry setting of the turbine. You can do drivability analysis, and particularly good to use together with the vehicle dynamics library. You can couple the drive shaft of the engine to a vehicle driveline model or a full vehicle model, and it uses a regular rotational connector, so it's really compatible with any rotational mechanical Modelica models. It will also, given the properties of the model, be suitable for software in the loop simulation together with engine control systems. So to the example use case, this is the engine that we modeled in this project. It's a 13-liter truck engine, which has exhaust gas recirculation and variable turbine geometry. And this one is certified for the post-new long-term emission legislation. If we look at the particular model for this engine, it looks like this. We have the air inlet path, there's a air filter, a compressor. Number 3 here is a simple charge air cooler model. There's a throttle, inlet manifold, the combustion engine and cylinder block. We have the exhaust manifold, exhaust gas recirculation like this. A particular EGR cooler, a simple model for that, which is based on this efficiency table that we saw earlier. So all the volume components also have the option to consider the thermal dynamics of the wall. So there's a solid mass component inside this volume and heat transfer between the gas and the wall. So you can see in the exhaust path that we have considered heat transfer between the gas and the wall, and then also heat transfer from the wall to the environment. Down to the left here, you can see the experiment that we have set up for this engine. And we've used a lot of table blocks to provide drive cycle boundary conditions for this engine in terms of both engine speed and fuel, injected fuel. Also valve positions for the throttle and EGR valve, and also the coolant flow rate and temperature. Also the ambient conditions have been specified from tables here, so the inlet air temperature is also specified. Looking at some of the results that we obtained, it looks pretty good. We can see the some properties here. We compare simulated values in solid blue and measured ones in dashed red. We can see that we have captured both the airflow rate, the EGR flow rate. The transient exhaust temperature is quite good, especially given the relatively low complexity of the heat transfer model. And the outlet nitrogen oxide, we have captured at least the transients pretty good, which is critical for exhaust after treatment system dimensioning. A lot more details on these models have been published at the latest Modelica conference, a paper by myself and a customer at Volvo. And you can also see a description of the methodology in this paper. So looking more at the contents of the library, we have an engines package which has both a number of templates for engine system models, There are also packages for different engine components, such as the cylinder, the turbo system, and then general type of fluid components like volumes and pipes, valves, and simple heat exchangers. There are also some fluid models, there are both mixes for exhaust and air by using the NASA expressions. And there are also simplified gas models assuming a linear CP for the gas. And that is good because that leads to a fully explicit model. So we do not have any nonlinear systems in this model either, which greatly improves in the performance. So that would be the end of this presentation. And I will now move to Taimola. And you may mention that notice that this is also version 1.1 alpha. This library do not have as many updates as liquid cooling do. There are a few new components and examples in this alpha, particularly aimed at providing very simplified models for control system development. So we have actually a customer who have used an engine model from this library and performed model predictive control based on that model. And that means that we have very few states in the system model. So the total number of states in that case was, I believe, 8, or at least less than 10 states for the complete system. So if you open the engines package, you find first some...
We don't see very much. I think you need to share your application.
Okay, sorry about that.
Much better now, thank you.
Okay, sure. Okay, so in the engines package to the left here, we have sub-packages for engine system templates. There are some example experiments that you can run. This is a simple experiment where we simply specify constant boundary conditions and put the ramp on the injected fuel. You can study the resulting torque increase and turbo speed up in that example. There is one example of how to specify dynamic boundary conditions from measured values, and the signals here are provided in a MATLAB file.
Sorry for interrupting, but I think you can do the trick of increasing the font size again.
I don't think I reduced them, but maybe we need to increase this some more.
Okay, that's much better, thank you.
There is also a template with an engine that can be replaced and a number of signals to be specified. Further on, there are cylinder combustion models. These are quite simple table-based and equation-based models. You can see also that the cylinder model is built up by a template that includes all the relevant mean value model equations, and the empirical part of the model can then easily be replaced in the diagram layer by including a table or some other empirical model. It would be possible to have a neural network model or a regression model, for example, or linking in an external combustion model from a function. So what you need to do is to provide values for all the real input connectors on this right side. So you need to specify the volumetric efficiency, the energy conversion efficiency of the combustion, the friction torque, and the exhaust gas temperature. The remaining connectors are then optional. The model can enable engine brake mode, and the model would then have to specify the torque and exhaust gas temperature that occurs during engine brake. In the turbo sub package, we have a compressor and a turbine. There are some new components that are named velocity here, since that have been added since 1.0. The difference here is that we do not have a state variable in the a variable in the connector for the angular position of the turbo, so that is not relevant in the case of turbo system modeling. And by using these components, there is one state that can be reduced from the overall system. I think these components should only be used in particular cases where the model must be kept at a very low number of state variables. In the volumes package, you find inlet and exhaust manifold components and also generic volume components. The manifolds are quite simple components where we have a gas volume and a capacity and heat transfer between the volume and the capacity. There is these components are conditionally declared, so either the components will be there or this direct connection of the gas volume to the external heat connector. There is also a particular component to convert between the air medium formulation and the exhaust gas formulation, so that these can be mixed in this component. There are also simple pipe components, and all of these components correspond to the generic ones that we saw in liquid cooling, so we do not have the geometric friction models here. A user will have to specify some flow correlation, for example, a nominal operating point or a loss coefficient for the pressure drop. It's also possible to enable heat transfer in this pipe, and if that is done, a user will have to specify the heat transfer area and also the model for the heat transfer coefficient. There are also some valve and heat exchanger models here. There is a butterfly device which has a flap in the gas path, and this position is controlled by an auxiliary force and the opening force of the flowing gas. This may be quite a special component that not everyone uses. Are there any questions on particular areas that I should focus on more within the engine dynamics library?
Doesn't seem so.
No? In that case, I think this would be the end of my presentation, and also for this library, of course, you are very welcome to come back to me with more questions. And of course, also customer feedback is very much appreciated.
Hi, Alex again. Am I still in time for just one question?
Absolutely.
Okay. I wanted to, I was wondering if you could show me at which point in your system you're actually feeding the emissions information down the exhaust, because I couldn't locate this point where you're actually outputting the emissions information. Please.
The emission information will have to go in this cout connector, and that may need a clearer name, I think. But this connector will output the emission information in the exhaust port, this port B. And it requires also that you have a medium model which includes trace components for the emissions. And that is available. There is one component for that, for example, this one, which has a number of extra emission species. But I will make a note of that and include an example with emission generation in the library. I think that would be a very good idea.
Leo here.
Yes.
How about switching off cylinders? So I'm not an engine expert, but there are a lot of new engines which do switch off cylinders. Can it be modeled with these libraries?
That's an interesting idea. It's currently the number of cylinders is a parameter, so technically no, but that would easily be attained by having that as an input.
Okay.
I think, but
and direct injection engine, is this supported?
We currently do not support it within this library. I think it's a limited amount of work that would have to be done to adapt it for that, but it's currently not supported in like an off-the-shelf product.
Because it was designed for diesel engine, so obviously you don't need it there.
No, exactly.
Okay, and the compressor model, can I use it as a supercharger or is it just for turbochargers?
The compressor could be used also for a supercharger. There are different kinds of formats that are, you would have to specify a compressor map for it, and there are different format options for that.
Okay.
And that could be either table-based, and we have actually added an equation-based cylinder compressor map model with 1.1 that handles better extrapolation to low rotational speeds, which is often a problem with tabulated values, that they do not cover the low speed operating points in the engine.
Okay, and if I use it as a supercharger, I have often these low speed working conditions.
You often have that actually on a turbocharged system as well, because on idling conditions, for example, the turbo speed is very low.
Yes, of course. Yeah. Thanks.
Thank you very much.
Okay, thank you very much, everybody.